Okay, let's do this question. It says find IO in the circuit using the node voltage method. So we have this circuit diagram and they want us to find the current IO, which is the current passing through this 1K resistor. Okay, so the first thing we're going to do is we're going to label our essential nodes and label our ground node. So I'm going to take this bottom node right here to be our ground node. And we should see we have one essential node up here. I'm just going to call this node 1. And we want the voltage at node 1. So I'm going to write the node voltage equation for node 1. We're always going to assume the current is leaving this node, going in these directions, right? Okay, let's write down the node voltage equation for node 1. We know we're assuming the current is flowing away from the node. So we're going to have the voltage at node 1 minus 12 volts. And that's going to give us the voltage across this 1K resistor. And we're going to divide it by 1000 to find the current flowing through that branch. Plus, we can see we have a current source. And this current source is flowing into the node. So because we're assuming that current is leaving the node, we're going to treat it as a negative current. So we have negative 2 times 10 to the negative 3. Plus, we have a current flowing away from this node here. So to find that current, we have to find the current in this resistor. So we're going to say V1 minus this voltage source. That's going to give us the value of the voltage across this resistor. And then we're going to divide it by 1000 to find the current. So we're going to have V1 minus this voltage source here, which is, they label it as 4KIX. So let me just rewrite this as 4000 IX, right? So 4000 IX, which means this is a current dependent voltage source. So this is a dependent source, but it is a current dependent voltage source, right? So we're going to have V1, which is the voltage at node 1, minus this current dependent voltage source. But notice, if the current is flowing in this direction, right? Look at the polarity of this voltage. The polarity of this voltage source is going to be from negative to positive, which means we're going to treat it as a negative voltage. So we're going to have the difference, which is V1 minus, and we're going to treat this as a negative voltage. So we have negative 4000 IX. All of this over this resistor here, that's going to give us that current. And all of this is going to equal 0. Okay, let's start to simplify this now. We know the LCD is going to be 1000, so we're going to multiply each term by 1000. And when you do that, that's going to give you V1 minus 12 minus 2 plus V1 plus 4000 IX. And all of that equals 0. When we simplify this now, we're going to get 2V1 plus 4000 IX equals 14. I'm going to call this equation 1, right? I'm going to call that equation 1. Now, because we had a dependent source, we must find that dependent variable, okay? So we know that variable, we know this is a current dependent voltage source. So we must find this dependent variable, which is Ix. So Ix is going to be the current flowing through this 1K resistor. Now notice how the current is flowing. It is flowing away from the voltage source to node 1. So even though we assumed when we wrote our node voltage equation that the current was flowing away from the nodes, that's just something systematic that we do. When we want to find the equation for that dependent variable, we're going to look to see how they labeled that dependent variable, okay? So because they actually have it going towards the nodes, that's how we're going to treat it. So we only assume the current is leaving when we're writing node voltage equations, all right? So we see the current Ix is right here, which is the dependent variable. Now to find that dependent variable, there are a few things we can do, right? Now when you look at this dependent variable, Ix, you can either perform KCL at node 1, or you can use Ohm's law to find the current that's going to be flowing through this particular branch. Now, when we think about it, right? If we use KCL, because we don't know IO, this really won't help us too much, right? Especially because IO is not in this first equation. So what we're going to do is we're just going to write Ix in terms of Ohm's law dealing with these two voltages, because we have V1 already in our first equation and we have Ix, which means this would be the best solution to go with when trying to solve this particular problem, right? So to find the current Ix, we know that's going to be Ix equals, and because the current is flowing away from this voltage source, we're going to assume that this voltage source here has a higher potential than this node 1, right? Now, because the current is flowing away from this voltage source, we're going to say that this voltage source has a higher potential than node 1, okay? So we're going to say that this voltage source has a higher voltage than the voltage at node 1. Now remember what we're trying to find. We're trying to find this current Ix, right? To find this current Ix, we need to know the voltage across this resistor. To find the voltage across this resistor, we're just going to take the difference in voltages between the source and node 1, okay? Because we know as this current starts to travel through here, some of the voltage is going to be left here and the rest is going to be at node 1. So if we can just subtract these two, we will be able to find out what is the voltage across this 1K resistor. So we're going to say Ix equals 12 volts, right? Because we're going to say, because the current is leaving that source source has a higher potential, minus the voltage at node 1 divided by the resistor, which is 1000. So I'm going to call this equation 2. Now, if you want to, you can actually write this into this equation and solve for V1, but I'm not going to do that, right? I'm actually just going to simplify this equation and use the matrix method. So I'm going to say 1000 times Ix, right? That way we get rid of that 1000 in the denominator. And when I simplify this some more, I'm going to bring this V1 over. So we're going to have V1 plus 1000 Ix equals 12, right? So this is my updated equation number 2, okay? So this is my updated equation 2. Now, when I look at this, I have two equations, two unknowns. So we can just use the matrix method, right? So I can say, I'm going to have a 2 by 2 matrix. So we know for the first equation, we're going to have a positive 2 and a positive 4000. The unknowns are going to be V1 and Ix. And for the first equation, it equals a positive 14. Now for the second equation, we have positive 1, positive 1000, and that's going to equal positive 12. So we're just going to take the inverse of A, multiply it by B. When we do that, we're going to get V1 equals 17 volts and Ix equals negative 5 milliamps. Okay, so we found V1, which is the voltage at node 1, and we found the current Ix. Now the question wanted us to find IO in the circuit. So IO is the current flowing through this 1K resistor. We know the voltage at node 1, and we know the current flowing through this 1K resistor. So to find the current IO, we can do a few things. We can either use Ohm's law, because we have a resistor between two voltage sources, right? So because we have a resistor between a node voltage and a voltage source, we can always find the voltage across this resistor, and we can just divide by the value of that resistor to find the current. We can also do a KVL loop on the outside, right? And we can also perform KCL right at this particular node here. So there are a few ways we can go about this. For this video, I'm actually going to use all of the methods just so you can see exactly how you can go about this. So I'm going to use Ohm's law first of all to find the current IO. So we know IO equals, we need the voltage across this 1K resistor. So because this resistor is in between a node and a voltage source, we know that to find the voltage across this resistor, we're just going to take the difference from node 1 and this voltage source here. Now because the current is flowing away from node 1 and into this voltage source, we can say that node 1 has a higher potential than this voltage source here. Okay, so node 1 has a higher potential than this point on the voltage source. So to find the voltage across this 1K resistor, we're going to say V1 minus this voltage source. So we have V1 minus, now this voltage source is interesting, right? Because notice what's going to happen. This current is entering this negative terminal here, which means this is going to be a negative voltage. So we're going to have V1 minus negative, that's going to be 4000 IX. So we have negative 4000 IX. And all of that is over 1000. Now we know the value of V1 and we know the value of IX. So when we simplify this now, we can say IO equals, we know V1 is going to be 17 volts. So we have 17 minus, or we can say plus 4000, and we have IX. We know IX is going to be negative 5 milliamps, right? So don't forget the milliamps. So we have multiplied by negative 5 times 10 to the negative 3. All of this over 1000. When we start to simplify this now, we're going to get IO equals 17 minus 20 divided by 1000. When you solve for this, IO equals negative 3 milliamps. This is going to be our answer for the current flowing through that branch. IO equals negative 3 milliamps. Now that's one way to solve this. Another way is we could have did a KCL at node 1, right? So let's do that quickly. Let me write it down. So we could have said KCL. Let me change colors. We could have said KCL at node 1, right? Now for KCL, we should remember the total current entering a node is going to equal the total current leaving a node. So in this particular situation, we know the current IX is going to be entering this node, and this 2 milliamp of current is also going to be entering this node. So we're going to say IX plus 2 milliamps equals, we know the only current we have leaving this node is going to be this current right here, the current IO. So we have equals IO. Now when we solve for this, we know IX is negative 5 milliamps, right? So I can say negative 5 milliamps plus 2 milliamps equals the current IO. When you solve for this, we can say that IO equals negative 3 milliamps. Okay? Okay, so this is our answer. So this was another way you could have solved with this problem. The final way you could have solved with this problem is you could have actually taken a KVL loop around the outer loop, right? Okay, now because we're going to take a KVL at the outer loop, we're going to walk around in a clockwise direction, right? So we're walking around in a clockwise direction and we're summing up voltages. So even though we don't have any voltage across this 1K resistor, well, both of these 1K resistors, we know the current and the value of those resistors. So what I'm going to do is I'm just going to label the polarities before we begin. So because the current is flowing in this resistor, I know the current is going to flow in the positive terminal and out the negative terminal for that resistor. And for this resistor, I'm assuming the current is flowing from from the positive terminal to the negative terminal. Okay, now let's start to write a KVL at the outer loop. So we have KVL, I'm going to use a different color, KVL at outer loop. So we're going to say that we're going to walk around, let's start at this 12 volt source. We're going to enter the negative terminal, right? So we're going to have a negative 12 plus, now the voltage across this resistor can be found by using Ohm's law. We can say the current Ix multiplied by the value of that resistor, which is 1000. So we can write plus 1000 Ix. Now when we look at this, we're going to continue in this direction, right? And we're going to enter the positive terminal once again. So the voltage across this resistor is going to be IO times 1000, which we can write as 1000 times IO, right? So we're just writing it in terms of Ohm's law. And our final voltage is going to be, as we continue to walk around, we're going to enter the negative terminal of this current dependent voltage source, and that's going to be negative 4000 Ix. And all of that equals 0. Okay, now let's simplify this. We're going to have 1000 IO minus 3000 Ix, and all of that equals 12. Okay? Okay, now remember, we're trying to find the value of IO, but we know the current Ix because we found it up here, which is negative 5 milliamps. So we're just going to put in negative 5 milliamps into this term right here. We're going to have 1000 IO. IO is what we're trying to find, minus 3000. We know Ix is negative 5 milliamps. So I'm going to say negative 5 times 10 to the negative 3, and that equals 12. When we simplify this, we're going to get 1000 IO. When we multiply this now, we're going to get a positive 15. So we have plus 15 equals 12. When you simplify this, we're going to get 1000 IO equals 12 minus 15. Therefore, 1000 IO equals negative 3. We want IO by itself, so we're going to divide both sides by 1000. We're going to get IO equals negative 3 divided by 1000. When you solve for this, IO equals negative 3 milliamps. So this is the current flowing through this resistor. IO equals negative 3 milliamps, right? As you can see, there are multiple ways to solve this particular problem. Once we knew the voltage at node 1 and the current flowing through this resistor right here, which we found using the node voltage method and writing an equation for the dependent source, we were then able to solve anything else we wanted to solve in this particular circuit, and they wanted us to find the current IO. So we were able to use Ohm's law, right? And we was able to find the voltage across that resistor because we know that node 1 would have had a higher potential than this voltage source, so we subtracted to find the voltage across this resistor, and we knew the value of this resistor, so we just divided by 1000. We calculated the current flowing through that branch. Now that was our first way. We also did a KCL at node 1, right? Because we know the total current entering a node must equal to total current leaving a node. We know we had Ix entering and we had this current source entering. So to find the current IO, we could have just used KCL. And our last way was we actually took a KVL at the outer loop and we wrote these terms, if it was a resistor, in terms of Ohm's law, which is current times resistance. So then we were able to calculate the current IO that way as well. So there are so many ways to calculate the current IO in this particular problem. I want you to see you have options, right? Whatever options you want to go with that way, because you're always going to get the right answer once you follow the right procedure and you do everything correctly. So if you have any questions, leave them down below. Stay tuned for more node voltage dependent source videos.